Hi, I'm Hoongyu Chong from Postec, and in this video I will present our work on differentiable point-based inverse rendering. Inverse rendering is the task of recovering the shape and material properties of a given object. To achieve this, we use multi-view images captured under various lighting conditions. These diverse lighting angles provide the necessary reflectance information to estimate a realistic bidirectional reflectance distribution function. Our approach reconstructs surface normals, material parameters, and visibility while considering self-occlusion based on the light direction. There are many challenges with previous inverse rendering methods. First, nerve-based methods suffer from long training times due to volumetric ray marching, often taking over 6 hours. Another challenge is the ill-posedness of limited light view angular samples. Accurate BRDF reconstruction necessitated sufficient light angular samples for realistic relighting. Previous works typically use images captured under fixed environment lighting, leading to inaccurate reflectance reconstruction. We present differentiable point-based inverse rendering (DPIR) on analysis by synthesis method that processes images captured under diverse illuminations to estimate shape and spatially varying BRDF. By adopting point-based rendering, we eliminate the need for multiple samplings in volumetric ray marching, significantly enhancing the training and inference speed. Our method achieves efficient and accurate reconstruction of geometry and BRDF through our proposed representations, including a shadow detection method using point-based shadow map rendering. We devised a hybrid point volumetric representation allowing discrete points to move in space while sampling surface normals from a continuous sign distance function. This enables fast rendering and smooth normal reconstruction simultaneously. The regularized basis BRDF mitigates the ill-posedness of inverse rendering stemming from limited live view angular samples. It consists of a per-portion diffuse albedo and a specular reflectance component. The specular component is modeled with weighted specular basis BRDF by exploiting the spatial coherency of specular reflectance. We apply regularization to the specular basis coefficients to enhance the accuracy of reflectance estimation. We propose an efficient point-based shadow detection method to estimate point visibility. First, we assume virtual camera corresponding to input light source. We then perform slatting-based rendering of the points to the virtual camera. The resulting Z buffer computes point self-occlusion with following equation. If computed point depth is smaller than the sum of the first intersection point depth and threshold, point visibility is 1, meaning it is visible from the light source. Our shadow handling method efficiently and accurately computes point visibility with point-based rasterization. We compute the radiance for each point with the following equation. Once the radiance of each point is computed, we project the points to the camera viewpoints using point splitting. We optimize point position, point radius, and MLPs for minimize the following loss functions. L2 loss and seam loss are computed between the rendered image and captured image. SDF loss promotes the zero level set of the SDF lies near the point positions. We also apply specular coefficient loss for diffuse and specular separation. For stable optimization, we employ mask loss to align the rendered mask from the points to the input mask. This is the comparison for multi-view multi-light dataset and photometric dataset. DPIR outperforms previous state-of-the-art inverse rendering methods in terms of accuracy, training speed, and memory footprint. Here are the rendering results for multi-view multi-light dataset. We achieve high-fidelity geometry and reflectance reconstruction for real-world objects. We also achieve accurate relighting results with different light directions. We evaluate DPIR on a photometric dataset with co-located point lights. DPIR directly optimizes geometry and reflectance, enabling fast training and accurate reconstruction. The explicit point representation and rendering of DPIR enable convenient scene editing by simply modifying points and their attributes. We can swap the diffuse and specular basis BRDF of each object and perform intuitive geometric edits such as geometry removal or object merging. DPIR also supports environment rendering by accumulating reflected radiance for each light source in the environment map. Thank you for listening.